Morning, everybody. Before we get started on the next section, last time, the last slide, we had these problems. I told you to work on those during over the weekend, and so let's go over them real quick. So we start off with this alkyl halide. Let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. How would we name that? One iodopentane, right? And we're going to react that with sodium azide. So this reaction arrow, you can list things above the reaction arrow like reagents, for example. And this is called sodium azide. It's a molecule you should remember from general chemistry. And it's a salt. So the nitrogen has a negative charge, or one of the nitrogens has a negative charge. Overall, the N3 has a negative charge, I should say. And the sodium is positively charged. And how is this going to, what's the product going to be? What happens? The iodine? So we're going to form a nitrogen-iodine bond? We're going to make a nitrogen-carbon bond, right? So we're going to end up with this plus what? Sodium iodide, right, which is a salt. Spectator ions, for all practical purposes, we usually ignore them, right? And so that's a substitution reaction. You all should know a little something about sodium azide because every one of you probably own a little bit of it if you have an automobile. It's what's used in airbags. Airbags don't really have air, they have nitrogen, okay? And so sodium azide is the nitrogen source that gives rise to the nitrogen gas used to inflate your airbags. But it's really useful in organic chemistry. If you look at the Lewis structure of it, these terminal nitrogens are nucleophilic. So this is a pretty good nucleophile, and it can do nucleophilic substitution chemistry quite easily. Sodium azide is explosive, and so you have to be careful when you're working with it, but it's not too bad. The second one, we've got this bromide plus NH, and what do we got on there? Ethyl groups, and a reaction arrow, right? So number one, how are we going to name this alkyl halide? What's the parent? It's butane, and what are the substituents? We've got a methyl and a bromine, or a bromo, right? Okay, so say it. One bromo, 3-methylbutane, right? So we're going to do a substitution reaction because that's what we're studying right now, right? So how's this going to happen? What's going to function as the nucleophile? The nitrogen or the amine. And what did I not draw on there that we have to assume is there? Lone pair of electrons, right? And so we get a nucleophilic substitution. The nitrogen now is positively charged because it has 4 bonds to nitrogen, and the bromide, right, is out there as such. Okay, does that make sense? We'll talk about these mechanisms a little bit more today. What's another way to name these? Is this an amine? No. Why is it not an amine? All amines must have a what? A lone pair of electrons. That's a quaternary ammonium salt. Okay? And again, like I mentioned, quaternary ammonium salts can be useful as antibacterials. A lot of hand soaps contain them. And this is one way in which you can make these quaternary ammonium salts is through substitution chemistry. Really, if you look in industry, the vast majority of chemistry that they really do is sophomore level organic chemistry because it works really well, it's reproducible, high yielding, okay? So if you can do something simple, you try to do it. Which one? What's a spectator? No, the bromine's not a spectator at this case. It's a salt. So it's just a positive and a negative charge ionically bound together.
So it's in there with the nitrogen?
It is associated with the nitrogen, yeah. It's not a spectator in this case because it's part of the product. Now let's look at the last one, or as I should say, the last ones. What you should see here is this is actually what we would call a multi-step synthesis. Notice I have 2 reaction arrows, but I actually have 3 reactions overall. Because on the second arrow, I'm going 1 and then 2. So that's really showing 2 different reactions. Okay, so there's several different ways in which we can actually present information for you for reactions. Okay? So how do you approach a multi-step reaction? Left to right, okay? Even simpler than that. 1 step at a time. The biggest thing that you all will do is you will look at all this and you'll try to figure out what the product is. And you will make big mistakes doing so. Don't do that. 1 step at a time. Ignore all this. This is the first thing that you need to worry about. If you don't get that right, you can't get anything after that right. So it's very important that you look at that. Then you look at what happens when you take the product and react it with that. And then take the product from that and do this. You need to write it out. So let's look at it in detail. So we're starting with what alkyl halide? Do I need to put the 1? I don't, because no matter where I put the iodo, it's going to be 1 iodo. So we can just call it iodocyclohexane or cyclohexyl iodide. Either way would be certainly legitimate. And the first reaction is we're reacting it with Na plus, SH minus. Sulfur has the negative charge. Sulfur is what we call a supernucleophile. It will do a lot of nucleophilic additions very, very easily. So what's going to happen in this first reaction? And does what? Makes a what bond? No, not double bond. Make a bond to sulfur, right? Plus we get sodium iodide that we kind of ignore. It's salt that falls out of solution. So I've converted this from a alkyl halide to what's my functional group now? It's a thiol. So I go from something that has no odor to something that stinks to high heck. Okay? This stuff will really drive you out of the room. Okay? So that's the product from the first reaction. That's that first question mark. Okay? Now the second reaction is reacting this with sodium hydride. So that's the first step over that second arrow. Okay? What do we know about sodium hydride? Is it basic or is it acidic? H minus. Would that be an acid or a base? It's a base, and it's a pretty strong base. It has a pK of in the mid-30s. I forget the exact value, but it's in the mid-30s, so it's pretty strong, 35, 36, something like that. Okay, so it's a strong base. What do bases like to react with? They like to react with acids. Do I have an acid? I do. What's acidic? The thiol. The hydrogen on the thiol is acidic, right? Sulfur sits right below oxygen. We know that water's acidic. Would a thiol be more or less acidic? As we go down the periodic table, what happens to our acidity? It increases. So it turns out that thiols are actually substantially more acidic than alcohols or water, okay? So we're going to deprotonate this particular. So the base reacts with the acid. We end up with a stabilized anion. Plus we get hydrogen gas. It's a fun reaction. You get to see all kinds of bubbles that will burst into flames if they're around a flame. Okay? So this is the product of that first step. Just acid-base chemistry. Okay? Now, the second reaction, what are we reacting this with? iodoethane, right? Notice I didn't actually give you the formula. It's something that you need to be able to So now what happens? Okay. So the sulfur anion reacts, displaces the iodide, and you make a new carbon-sulfur bond. And you get that molecule. So we went from an alkyl halide, and we did a functional group transformation to a thiol. We did some acid-base chemistry and made what we call a thiolate, which is just the anion of a thiol. And then we did substitution chemistry again, and we got what functional group? Sulfide. So we go from an alkyl halide to a thiol, to a thiolate, to a sulfide. Okay? Any questions about these?
So if it's got like one, I don't know what to call it, one compound above the arrow, one below the arrow on the second part.
Oh, okay.
So does that mean it's a two-step reaction?
It does.
Okay.
If I didn't put 1 and 2 here, then you would have assumed that I would have treated this with a mixture of sodium hydride and iodoethane all at the same time,
So if it doesn't
which wouldn't have worked here, okay? So that's why 1 means do that first, followed by this.
So if it doesn't have numbers, it is a mixture, because there's so many questions.
If it-
that, I'm like, what does it mean?
If it has no numbers, then it means it's all together.
Okay.
And that may be okay, it may not, depends on what you're trying to do. Okay, so if I had just this, it would mean that, yep, sodium hydride and iodoethane were present at the same time. This means that they are not. First this, then that. Okay, does that make sense? Good.
Where did the iodine go?
I did not draw it. What would it end up being? It would be sodium iodide. Yep, it would be a salt that would fall out. Good catch. So today, we're going to talk a little bit about the mechanisms of these reactions. So up to this point, I've shown some arrow pushing, but we haven't really gotten too deep into it. So today, we're going to finish up talking about the actual mechanisms of these substitution reactions. Because as you can imagine, there are at least a couple of different ways that you could put on paper for how these reactions actually occur. And I'm going to show you how those are, and then we're going to talk about some of the reaction parameters that we would look at to determine which one is actually being utilized for a variety of different reactions. Okay? So we know what nucleophiles are, right? What was the golden rule that I told you the other day? All nucleophiles are Lewis bases, but not all Lewis bases are nucleophiles, right? And so this particular slide shows that quite nicely. Right, a nucleophile will actually attack an atom other than hydrogen. For organic chemists, 99% of the time this is carbon. Right, so the nucleophile will attack a carbon atom, but a base will attack a proton and remove a proton. Right, that's what distinguishes a base from a nucleophile. There are nucleophiles that can function perfectly as bases, and they can compete with that. There are bases that will never readily behave as nucleophiles. And then there are nucleophiles that just really don't behave as bases at all. Okay? I do not expect you by the end of this course to have all of that I have in my head in your head. You're not going to have it. Okay? It takes years of experience. But you're going to have to start thinking about what makes something a good nucleophile versus what makes something a good base. And there will be some things that we talk about throughout the semester that should make that a little more clear. But in both cases, nucleophiles and bases both have a lone pair of electrons. Okay? That's what we're looking at. You need a lone pair of electrons or a pair of electrons. I shouldn't just say lone pair because double bonds can also function as nucleophiles that we'll see later. But you need a pair of electrons. Okay? And so here's an example of an alkyl halide reacting with something that behaves like a base. Okay? Notice what's happening. The base is attacking the hydrogen. The electrons between the carbon-hydrogen bond are coming between these two carbons, and the halogen is leaving. Okay? So we're going from something that has all sigma bonds to something that now has what? Pi bonds, right? Double bonds, pi bonds. So what are we doing here? Is that a substitution? What is it? That's an elimination, right? And so you'll find that substitutions and eliminations kind of go hand in hand. However, here, the nucleophile, right, the thing with the lone pair of electrons is actually acting as a nucleophile, and it's attacking the carbon atom, not the hydrogen. Okay? And so we're forming a new carbon nucleophile bond, whereas here we were forming a new carbon-carbon pi bond. Okay? Now, it turns out that nucleophilicity and basicity are related, but they're not the same. Okay? They are related, but they are not the same. And that makes some sense, right? Because all nucleophiles are Lewis bases, but not all Lewis bases are nucleophiles. So they all share the ability to donate a pair of electrons to something, be it a proton or be it a different atom, right? You need to know what distinguishes a base from a nucleophile. So when we're talking about something as a base, we're talking about its basicity. And we're talking about how readily it donates its electron pair to a proton. Okay? The way that we characterize this, the way that we determine whether or not something is a good base or not, is through thermodynamic parameters. Okay? Through equilibria, right? If I react a strong acid and a strong base, you know that the equilibrium lies to the left or the right. Reactant side or product side? Product side, right? And so you would express that as a Ka. But do we think about things in terms of Ka? What other parameter do we use? pKa, right? We use pKa. And so things with really high pKa values are strong bases or weak bases? High. Large values. They are strong bases. Things with very small pKa's are, okay, they're the anions of stronger acids, that's true, which makes them weaker bases, right? So that's good, right? But it's all thermodynamics. However, when we're talking about something being a good nucleophile, we're not talking about which way the equilibrium lies. We're talking about how fast it reacts. Notice I told you earlier that thiols, the sulfur, is a supernucleophile. That means it reacts extremely quickly with alkyl halides or other electrophiles. Okay? The rate of that reaction is quite large. And so here we're talking about a rate constant. Okay, so if something is a poor nucleophile and you go in and you try to do the reaction, you would expect to be in the lab for a long time if you had to wait for that reaction to be over. Right? But if I gave you a really strong nucleophile or a supernucleophile, you would expect that that reaction would be over relatively quickly. Okay? And it's a relative argument. Okay? Just because sulfur is a supernucleophile doesn't mean it may not take an hour or two for the reaction to go to completion. It just means that it's so much faster than any other nucleophile that we can think of for that particular reaction. Okay? So these are the fundamental differences that you see between bases and nucleophiles. Some of the common nucleophiles that we use in organic chemistry are listed on this table. There are oxygen, nitrogen, carbon, halogen, and sulfur-containing nucleophiles that are very, very useful for us. You need, by the end of tomorrow, you need to have this table memorized. Okay? You need to know these nucleophiles. It's just a handful. Okay? We have negatively charged nucleophiles, and we have neutral nucleophiles. Okay? Oxygen-containing nucleophiles, hydroxide, alkoxide, acetate anion. This is the salt of a carboxylic acid. This is the salt that you generate from an alcohol. And this, of course, comes from things like sodium or potassium hydroxide. In all cases, the oxygen atom bears a negative charge. Okay? Notice we also have some neutral nucleophiles that contain oxygen, water, and alcohol. Oxygen in both of these molecules is neutral. Which one would you expect to be a stronger nucleophile, hydroxide or water? hydroxide, because it's negatively charged. Negatively charged nucleophiles almost always are stronger nucleophiles than their neutral counterparts. Okay? Nitrogen. Nitrogen-containing nucleophiles. N3-, azide. Very good nucleophile for making carbon-nitrogen bonds. Okay? But there are also some neutral nucleophiles that contain nitrogen, like ammonia, or primary, secondary, even tertiary amines. They just don't show them all up here. So amines make pretty decent nucleophiles, as does azide. Azide is a pretty darn good nucleophile, actually. Okay? It will do chemistry about as quick as sulfur will, really quick. And then there are carbon nucleophiles, where we have carbon with a negative charge. Things like cyanide or acetylide make really good nucleophiles. Now, if we draw out the Lewis structure for cyanide, what you notice is that both the carbon and the nitrogen have a lone pair of electrons. Which one of those atoms bears that formal negative charge? Okay, how many electrons does nitrogen come in from the periodic table? 5. And how many does it formally own here? 5. So the formal charge of this is 0. How many do we come in with for carbon? 4. And how many does it formally own? 5. So carbon actually bears the negative charge. Okay? Now, this is an excellent experiment for you all to try at some point in your life. Okay? If you take cyanide and you react it with an alkyl halide, what you will form is a carbon-carbon bond, not a carbon-nitrogen bond. So, for example, if we used iodoethane, it would be the carbon atom that would attack the other carbon, and you would end up with this molecule. It's not the nitrogen that behaves as the nucleophile, although it has a lone pair of electrons, just like carbon does. But what distinguishes the carbon from the nitrogen here? The formal negative charge. It makes it the stronger nucleophile. It's a perfect example of how charge matters. There's some other things about where the position is on the periodic table, but we don't need to go into that right now. Okay? So the negatively charged atom. And by the way, we just formed a carbon-carbon bond in this reaction. Forming carbon-carbon bonds is the most difficult thing in organic chemistry. There's only about 6 or 7 real ways to do it. And people have been studying it for 100 years. And people have won Nobel Prizes on finding new ways to make carbon-carbon bonds. It is the most difficult thing. It is what we have to worry about when we're putting things together. How are we going to make the carbon-carbon bonds that we want to make? And one of the ways that we can do that is by reaction with cyanide. What do you all know about cyanide? It's very toxic, right? So we're not going to let you all do any chemistry with cyanide in the lab, okay? But it is a very good nucleophile, and we use it quite a bit in my laboratory to make carbon-carbon bonds. Okay? Halogens also make pretty good nucleophiles. Notice there's no neutral versions of the halogens that function as nucleophiles. I2, Br2, and Cl2 are not nucleophiles. They are electrophiles. Okay? They want to accept a pair of electrons, but iodide, chloride, and bromide are pretty decent nucleophiles. What do you think about the nucleophilicity as we go down the periodic table? Does it increase or decrease? It increases. As you go from chloride to bromide, the nucleophilicity increases. As you go from bromide to iodide, the nucleophilicity increases. Okay? So as we go down the family, the nucleophilicity increases, just like when we looked at oxygen and sulfur. Okay? As you go down the periodic table, usually the nucleophilicity increases. And then, of course, the sulfur nucleophiles that we talked about earlier, and then we have the neutral versions of these. Okay? Most people will be fairly comfortable doing the thiolate chemistry that we're talking about here, because thiolates, being salts, they're not very volatile, and they don't stink as bad. These things, I mean, really, really stink bad. Okay? So if you've ever smelled a rotten egg, that's because of the dihydrogen sulfide that's present. There's very, very little dihydrogen sulfide present, but it stinks really bad. Okay? So that's why they use these types of molecules to lace the natural gas supply with so that you can smell, because natural gas you can't smell really. So they have to lace it with a phial of some sort. Okay? So let's talk about the mechanism of these nucleophilic reactions. Okay? When we're talking about a mechanism, we're asking what bonds are being made, what bonds are being broken, and in what order does that happen. Okay? If we look at this particular reaction, we're going to break this sigma bond, and we're going to generate this sigma bond. But what's the order in which those get formed and broken? That's really what we're interested in mechanism. Okay? That's what we're interested in mechanism. And there's three ways in which we can envision this reaction occurring, at least on paper. We could imagine that the nucleophile will attack the carbon and the halogen will leave at the same time. That's how I've been pushing these arrows up here so far. Okay? So what do we know about carbon? Carbon can have how many bonds? It can have 4 bonds. Can it have 5? No, because of where it sits on the periodic table. It doesn't have the orbitals to have 5, right? So if I'm going to form a bond between this nucleophile and this carbon atom, I must be breaking this bond between the carbon and the halogen at exactly the same time. Okay? And the way that we think about it is I'm forming a partial bond between the nucleophile and the carbon at the same time that I'm partially breaking the bond between the carbon and the leaving group, or the halogen. Okay? And so we kind of consider those half bonds. It's kind of a hand-waving kind of thing, okay? And so we say we're making bonds and breaking bonds at the same time, okay? The rate of this reaction follows this rate expression. It is known as a second-order rate equation. What does it mean to be second order? What does the order of a reaction rate mean? What does it tell us? You all did this in general chemistry. You determined reaction orders, right? Remember? That's why that course is a whole prerequisite to this one, right? Right? It's a second order rate expression. Okay? It means that in the slowest step, both of these species are present in that slowest step. Remember, the rate expression, the rate doesn't tell us anything that happens after the slowest step. It's all about the slowest step that determines the rate of the reaction, right? Right? So what is this telling me? What is this expression telling me? Don't worry about the equilibrium or the rate constant. We're not interested in that. What do these two things tell me? Happens at the same speed. They're both important, okay? What do those brackets mean? Concentration. Well, we don't know that it's the same concentration yet. I haven't told you, but it tells me that it's dependent on both the concentration of the alkyl halide and the concentration of whatever the nucleophile is, right? So if Anna comes in and runs this reaction where she has 1 molar alkyl halide and 1 molar nucleophile, she can determine the rate expression, right? But then let's suppose I ask Shelby to come in and double the concentration of nucleophile. What would we expect that reaction rate then would be? So he had 1 molar alkyl halide just like Anna did, but now he's got twice the concentration of nucleophile. Well, you will run out of alkyl halide first. It's the limiting reagent, that's true. Okay, but it's going to still affect the rate. So what's going to happen to the rate in his particular reaction? Increase by how much? It's going to double. His reaction rate will double just by doubling the nucleophile concentration. Now I asked John to come in and double the concentration of alkyl halide and double the concentration of nucleophile. What would happen to his rate? If he doubled it and doubled it, go quadruple the rate, right? The rate is dependent on both the alkyl halide concentration and the nucleophile concentration. And it is first order with respect to each one. Why is it first order? Because only one species I only need one of these and one of these in the rate determining step. All those numbers that you calculated from your experiments in general chemistry were telling you something about the molecularity of the reaction. How many of these species had to come together for this reaction to occur? Okay? Did you all learn that? Or did you just figure out how to solve the math? Pretty much so figured out how to solve the math, right? Okay. Because that's what was on the test. That's great. Okay? So, this is actually known as the mechanism for an SN2 reaction. SN2. Big S, little n, 2. What does that stand for? S stands for substitution, N stands for nucleophilic, and what's the 2 stand for? Well, pretty close. It stands for bimolecular, meaning you have one of each species that are responsible. So it's a second order reaction, so you weren't far off. Okay? So that's what's happening here. This is a second order reaction. The nucleophile is attacking the electrophile. It's all happening in the rate determining step. I got to have this, and I got to have this. So if I have 1 molar, I'm going to have one rate. If I double one of them, I'm going to double the rate. Okay? So that's an SN2 reaction. But there's something else that we can think of. I can imagine a situation where the leaving group will leave and break this sigma bond first and generate what's called a carbocation. Okay? Is a carbocation stable or unstable? Unstable. It is unstable. And why is it unstable? Pardon? 6 valence electrons. That's right. It does not satisfy the octet rule. Right? What's the hybridization of a carbocation? Here we were sp3. What's the hybridization of this? It is sp2. It has a p orbital that is vacant, that has no electrons in it. And that carbon atom is positively charged. Okay? Now, it turns out that carbon sits in a very special place on the periodic table. I've told you that multiple times. It's not too close to fluorine, and it's not too far away. Okay? And so it can actually have fewer than 8 electrons for a little while. Okay? You cannot bottle these types of carbocations in a bottle and put them on a shelf and use them. They react very, very quickly. Okay? They're not stable as is. So you can imagine that this leaving group will leave, generating a carbocation, and then the nucleophile attacking to form the new carbon nucleophile bond. But what you'll notice in this particular case is that the rate equation is first order. So if I ask Anna to come in and run this reaction, where she's got 1 molar alkyl halide, 1 molar nucleophile, she finds out that she has some particular rate. And then I ask Chase to come in and double the amount of nucleophile, what would he notice with the rate? Nothing would change. The rate does not change if we increase the nucleophile concentration. Okay? So what must be the slow step? The first step, the formation of a carbocation. Does that make sense? Why should the first step be slower than the second step? Well, that's a true statement. You're only as fast as your slowest step, but why is this step, why does it make sense that this is the slow step and this is the fast step? Well, that's true. What do we know about breaking bonds? You're right on it. It takes energy. All bond-breaking events require energy, right? And I told you that you probably learned in your biology classes or when you get into biochem that they'll talk about ATP being broken and releasing energy. That's nonsense. It doesn't happen, okay? There are other events that happen that lead to the release of energy. All bond-breaking events are endothermic by definition. If you look at the energy diagrams, they're all endothermic. But what's happening in the second step? We're bond making. And what do we know about bond making? Endothermic or exothermic? They're exothermic. Very good, right? And so it makes sense that this is the slowest step. Makes perfect sense. Okay? This is called what? This mechanism is S what? SN1. Substitution, Nucleophilic, unimolecular. Some people say monomolecular. It's unimolecular, okay? It tells me that one and only one species is involved in the rate determining step. And that species is the electrophile, in this case the alkyl halide. Okay? Now, there's a third thing, at least on paper, that we can think of. And that is that the nucleophile attacks the carbon first and forms this complex, and then the leaving group leaves. This makes no sense in organic chemistry. Why? Carbon can only form 4 bonds. And this one requires that carbon has had how many bonds? 5. When you get into inorganic chemistry, things like silicon, they can do this type of chemistry. You can have an addition followed by an elimination. Okay? But if you think about it, we're no longer in the second period. We are not beholden to the octet rule anymore. We have more orbitals. We have things that electrons can be shared to. Okay? So while you will learn about this type of mechanism if you're a chemistry major when you get into P-Chem and inorganic chemistry, for organic chemistry this makes no sense because carbon sits on the second period. Okay? So yes, I can draw this out on paper, but it makes absolutely no sense given what we know about carbon and the orbitals that it has. Okay? So this third possibility, just put it out of your mind for right now. Okay? We can have the nucleophile attacking the carbon as the leaving group is leaving, and that would be what? SN1 or SN2? SN2. And we can have the leaving group leave to give a carbocation intermediate, which then gets attacked by the nucleophile. That's SN1. Okay? Now, how do these reactions look in terms of a reaction coordinate diagram? You all remember these from general chemistry? Okay? This is the energy of our starting materials. This is the energy of the products. This is delta H, right? So this is a thermodynamic parameter. This is all about equilibria. So the greater the distance here, the more the equilibrium lies to the right. The shorter this distance, the more the equilibrium lies to the left. But what's this business? EA. What's EA stand for? That's right. It's the energy of activation, or the activation energy, right? It is what determines our rate. Okay? Is this an SN1 or an SN2 reaction by looking at the diagram? It is SN2. And how do you know that? Okay. So my nucleophile is coming in as my leaving group is leaving. That's what these dashed wedges mean. Okay? So how is the nucleophile with respect to the leaving group here? Geometrically. Describe a bond angle for me. It's 180 degrees, right? The nucleophile comes in from the back. And in organic chemistry, you will hear organic chemists refer to this as backside attack. Like I said, organic chemistry, developed by males, very violent. Okay, we say attack a lot. Okay? But the nucleophile is attacking the carbon atom 180 degrees to where that leaving group is. Does that make sense? You're shaking your head yes. Why does that make sense to you? It's correct, so but why does it make sense? Okay, so, well, they're not both negatively charged, but they both have electron pairs, right? So here the nucleophile has a negative charge, but it's got lone pairs of electrons, right? The bromide also has lone pairs of electrons. Are those electrons going to want to be close to one another? No. How can I get them as far apart as possible? 180 degrees, right? So that's the simple explanation that I love. But for those of you who will take Dr. Wallace later, he hates that explanation. He likes to use the molecular orbital explanation, which is the absolute correct explanation for this. Why does it make sense on a molecular orbital basis? Let's see, we're at enough time. Oops, I'm sorry. if I think about this carbon, and I'm just going to put some bonds out here. We don't really care what's there. Here's the halogen. Okay, it's this bond that we're interested in, right? We're interested in replacing that bond with some type of nucleophile, right? Everybody agree with that? Bonds are actually orbitals. Okay? This is a bonding orbital. So bonding orbitals, we can also have what other types of orbitals? You had bonding, you had non-bonding, and you had, come on, we need to, come on, let's get our gen chem back, okay? We had bonding orbitals, we had non-bonding orbitals, and we had anti-bonding orbitals, remember? Anti-bonding orbitals, you're talking about breaking bonds. This is a bonding orbital, but you also have an anti-bonding orbital where the orbital lobes are on opposite sides of the molecule like this. So what is the nucleophile really putting its electrons into? Where's it going? Into the anti-bonding orbital. And as those electrons are going into the anti-bonding orbital, what does it do to the bond of the carbon halogen? It stresses it or it breaks it, right? So remember your molecular orbital diagrams? The cool thing is in organic chemistry, we can push electrons and account for it. Okay? And so I like to think of it as it just comes in and kicks the leaving group out. But it's all orbitals. So you have a bonding orbital, you have an anti-bonding orbital, and the nucleophile donates its electrons into that anti-bonding orbital, which then breaks the carbon-halogen bond. How many steps are in this particular mechanism? 1. SN2 has a single step. People get this confused all the time because they see the 2 and they think, oh, that means 2 steps. It means bimolecular. Both species are coming together in a single step to do this reaction. Okay? Now, if we use some of our information from Chapter 5, we know that if we start off with a chiral molecule, in this case a chiral alkyl bromide, okay, so we have a particular configuration, either R or S, okay, depending, let's just say this is like a methyl group, right? Hydrogen would be the lowest priority. Bromine would be the top priority. That would be number 1, that would be number 4. Why would we number these? Carbon versus deuterium. What would be number 2? Carbon, and then deuterium. So deuterium would be number 3, right? So we would go 1, 2, 3. That's going in which direction? That's the S isomer, right? If the nucleophile is doing SN2 chemistry, it attacks from the back side. The leaving group is leaving. Notice in the transition state, this carbon atom kind of flattens out and looks like an sp2 hybridized carbon, okay? And then as the leaving group leaves, you form this molecule, okay? So what happens to the stereochemistry? It is inverted. So if we start with the S stereochemistry, the product must be R, and it's 100%, okay? It is 100% inversion, okay? So the nucleophile comes in, we go through this transition state where the carbon atom is fairly planar, and it inverts. This is just like carrying an umbrella without the little flaps in it, right? And the wind catches it and it inverts. So you go from something that repels water off of you to something that sits there and holds water like a bowl. Okay, same kind of thing is happening here. And in fact, chemists will call this umbrella inversion. Okay, so that's what's happening. Okay, so for example, if we look at this particular molecule, right? Thiolate is attacking, leaving group is leaving. We've inverted the stereochemistry. We've inverted the stereochemistry here as well. You can show, look at the models and you can see that that is true. Okay. SN2 chemistry has a lot of uses, especially in the pharmaceutical industry. And like I mentioned, pharmaceutical types really like to use stuff that you learn as a sophomore because the chemistry works really, really well. Okay. But you take some molecules like this and you can put them together quite easily and make ethambutol, which is useful in the lungs for a variety of ailments. But it's nothing more than 2 molecules of a nucleophile attacking this dihalide. So you've got basically two alkyl halides that are just connected together, and you form these new carbon-nitrogen bonds. Now notice, oxygen and nitrogen are both present. Oxygen also has a lone pair of electrons, but it's not oxygen that's doing the chemistry. Why? Why is it nitrogen and not oxygen doing the chemistry? Oxygen also has a lone pair of electrons. Actually, it has two of them, right? So why is the oxygen not functioning as the nucleophile, whereas the nitrogen is? Nitrogen does not have a formal charge there. What do you know as we go from left to right on the periodic table? Does electronegativity increase or decrease? Increases. So what's more electronegative, oxygen or nitrogen? Oxygen. So oxygen being more electronegative, is it wanting to hold on to its electrons more, or is it wanting to share them more? It wants to hold on to them. Nitrogen being less electronegative is willing to donate them. Okay? This also turns out to be pretty useful in this particular reaction. Okay, so you take this alkyl iodide, react it with methylamine, you form this carbon-nitrogen bond, and then in one step you make Prozac. 2 steps make Prozac a multi-billion-dollar drug. By the way, all sophomore-level organic chemistry. Okay? What's really tricky is, does it also contain chiral centers? It does, right? It has one chiral center. And why it's so expensive is that it has to be one enantiomer. Okay? So making Prozac is real easy. Making one enantiomer of Prozac, not so much. Okay? And so that becomes the challenge. All right, so we'll finish this up. I've got stuff I need to hand